All right, here we are. All right, let me put this on slideshow and let's get started. So again, welcome to this afternoon. This is the Unit 7 webinar for chemistry. Thermochemistry is our topic tonight. I am recording so that folks who are not able to attend can watch it later. Andrea and I are co-hosting tonight. She's running a little bit late, but she'll be here as soon as she can. And we're just going to go ahead and get started. I particularly love these two images that are on the front screen. There's just on the left, there's just so much to think about in that picture, and it hits so many of the things that we're talking about across the year, not just in this unit, but also in Unit 1. We do a lot of kind of climate change concepts, sea level rise, et cetera. So it just kind of brings it back full circle. You know, we start the year with that in Unit 1, and then we kind of come back to it in our last unit of the year. The one on the right I like a lot also, and then I'm always fascinated by the date of that. So 2007. You know, we've been talking about climate change for a long, long time, and sometimes for our students, it's just like they just heard about it, you know, last year or 2 years ago or something. It's like I like to remind them, like, nope, it's been a thing for a while now. So, anyway, just wanted to start with those two pictures. All right, here we go. So, could you please, if you have not already, could you please check the name that shows up here in Zoom as, does that have your actual name on it? Like there's someone here named iPhone. Is it possible, iPhone, to change your name just so if you come up with a comment in the chat or want to chime in, we know who's all here. So that would be great. Just click on the more button and then rename. But I see most of us have names here. So that's great. And then also, we're taking attendance now with the Google form, so it's linked, but you know what we need to do is put the link to the slides in the doc or into the chat. So let's do that right now. And where did my chat box go? Here it is. All right, so there's the slides. And let's catch back up to where we were. So attendance is taken using that Google form, so you can just click right on that link. In order to be counted for attendance, you have to be registered for the webinar. So if you're not yet registered, there's the link right there for the Wild Apricot, and you can go ahead and register yourself. Just a reminder, if you haven't heard this yet, that there is a cap per quarter on PD funds that are spent. So I believe the amount is, $400. I don't have it written on this slide, but we've just started a new quarter. So hopefully you are all just at the start of your accruing your 400. So again, thank you for being here. I'm looking forward to talking about thermochemistry. It's one of my favorite units. People are still rolling in here a little bit, but we're going to keep going. If any questions come up along the way, go ahead and throw it in the chat. I've got that open, so I'm going to try to keep an eye on that. Takes me back to my CDL days when it was like, you remember it, how it went? You were like trying to present, check the chat, and all the things at once. So doing some of that tonight. Okay, so anytime we're looking at a unit and thinking about not only like the student activities, but the thinking that we're asking students to do, all comes back to the design principles, the patterns design principles, which there are 8 of them. They're all here. If you haven't had a chance to read through this document or really think about each of these things, it really helps to tie together the thinking behind the design of not only the curriculum, but the sequencing of things. Why do we have data discussions? How are we getting students to talk to each other? How are we engaging in inquiry? you know, all of the units in the curriculum have these common principles woven in through the planning of the curriculum. So I always like to start with this slide. Just if you haven't seen it for a while or maybe have never seen it, it's worth a read because it does really kind of connect the dots and tie all the pieces together. I'm not going to go into each of the links right now, but I wanted you to know it's here if you want to do a dive. Links, please. Let's try the link again. Thank you for reminding me. Here it is. And the slide number 3 or so is where the Google form for attendance is. So you can click on the link there. All right. Last comment on this slide. The one that's resonated with me is number 3, the patterns approach to inquiry. And this, in particular, this diagram right here, which shows up on almost every lab that we have, certainly in chemistry, shows up on almost every lab. And I go through this sequence with my students. Like, we start with a wild guess. We literally do not know the answer because we don't have any context for this experiment. We have not worked with this material at all, so we are literally guessing right now. Then we go into our lab and we collect some data. We're looking for the patterns that exist in the data. We're making sense of those patterns by talking it through with each other. And then we're applying that pattern not only back to our original wild guess question, but also to any future questions that we have about materials that we can apply this pattern to. So at the end, it's no longer a wild guess, right? Now we have context, now we have a pattern, and we can apply it to a new situation. So really talking about that process with students and helping them see like, oh, we do this every time. Like this process is a real thing. Like this is what scientists do when they think about when they're trying to answer a question and they're collecting data and looking for a pattern. And then once they have that pattern, they can apply it in new situations. So just they are scientists, right? They are doing the work of scientists. So really just reinforcing that with them, it was very powerful for me and my students. So that's just something that I keep coming back to is this idea of inquiry approach. Keeping my eye on the chat. Okay. So Unit 7. So we still have this distance learning unit planner. This is useful if sometimes if you're looking for example, if you know you're going to be out one day and you're looking for some subplans and sort of students can self-navigate through the material, there's some good stuff on the distance learning that you could use. There's also some videos on there. So I like to point out it's still there, right? The distance learning unit planner is still there, still useful, but most of the time we're looking at this one. So here's the in-person unit planner. And probably you are not new to patterns, but if you are, all of our unit plans are really similar. So we have our resources at the top, including our walkthrough of the unit. We're going to look at that in a second. The vocab that we're going to be talking about in this unit, how to do a whiteboard meeting. What are some resources for asking students to do CERs? Here's the rubrics for this unit and other useful posters and things that you may need are all linked here, including the essential question for the entire unit and which NGSS standards are connected to this work. Then we go through our different task sets, and these are meant to happen chronologically. So we start with task set 1, which is almost always the opener for the unit, starts us off, gets us thinking about some of the concepts, and then we progress through the task sets, and then we usually have an assessment or engineering at the end of the unit plan. So that's kind of the overview of what it looks like. And I want to click here. So these two are probably the most often used in our resources. So the unit walkthrough is great because it does kind of a snapshot overall I don't see anything in the chat. I'm just doing a quick double check though. Can you guys see this document? My green square has gone away and I'm not sure if only you can see the slides or can you also see this document? Can someone let me know in the chat what you're able to see? I can see. Great. Thank you so much. Okay, so back to our walkthrough. So this gives you, great. Thank you so much. This gives literally an overview of what's happening in each task set, and then what's linked down here are the teacher notes that go with it. So what are we wondering about? What's our question about for this task set? And what should students know as they're coming in? And what do we want them to learn by the time they're done with that task set? So again, just an overview, quick overview of what's happening in each task set. And then the more kind of specific details show up in our teacher notes. Now, if you click on the teacher notes and it says restricted access, what that means is you will need to fill out a Google form where you're requesting access to our restricted folder. The restricted folder, I'm just going to show you right now, just while I have you here as a captive audience. The restricted folder is in, and the open access folder are in, oh wow, let's see, sorry, I am not in the right account. Okay, let's try that again. They are in shared drives. So formerly they were elsewhere, but now they're in shared drives. And here they are right here down at the bottom. PDX STEM, Patterns Chemistry, Open Access. These are all the files that anyone with the link can see them. The restricted access, these are all files that we want only teachers' eyes to see. So we don't want students getting into these folders because often we have the key in there. We have tips and strategies and tricks. It's meant for teachers. It's kind of teacher talk about how to progress through the task sets, etc. So if you are not able to access this and you're looking in the right space, you're looking in shared drives, and then you're looking for that restricted access. If you're not seeing that or you can't access the documents, then you probably need to fill out the Google folder, or sorry, the Google form link. And that's just where we confirm that you are a teacher in a district. And then once we confirm that, then we can add you to have access to the restricted folder. I noticed that Andrea is here right now. Hello, Andrea. Andrea is my co-host. Hello. Andrea, would you be willing to drop into the chat the link for the Google form to request restricted access?
I will look that up and put that in there in just a moment.
Excellent.
And also, it looks like a link for the Google Drive. Yeah, I'll see what I can find. Yeah, I'll be there in a second.
Thank you. All right, continuing along. So this is just what the unit overview does. It goes through each task set, etc. Gives you an idea of like how many days will I be spending on this? 1 day here. The engineering project is always, 3, sometimes longer days, but the unit walkthrough is a great place to begin because it does give you that kind of big picture overview, like where am I starting, where am I ending up, and understanding the sequence of events that lead us through the unit. The other great document is the INB. Now I'm going to tell you right now, the INB is not currently updated. We've made a couple of adjustments in Unit 7, specifically mostly to the fuels lab. And what we have not had a chance to do yet, and this is true for many of our units actually, this summer's work is one of the things is going to be updating our INB. So if you're using the INB, please know that there's a couple of parts on the INB that are not yet updated, but we're going to be kind of doing a big dive into that over the summer. But the INB is, there's people do a range of things. Some people really use the INB a lot, and that's the notebook for students, and that's where they're recording notes. But then there's also opportunity for them to do some individual practice or thinking or responding to something in their own words, their own their own sense making, if you will. So I like the INB for that reason. Um, and some people just do kind of, class notebooks on their own. Whatever works for you is great. You should do that. But this is a resource that is out there in case you're interested. All right, let's go back to our slides. And anytime if you have a question, please go ahead and add it to the chat, and we will just keep it informal and pause as we need to hear questions, be able to respond to questions.
Christy, would you drop the link to the slides in the chat just so that if anybody does have anything and I need to drop additional links, I can do that?
I will. Let's see if it's this one. I think it's this one, presentation. Yeah, I think it's this one.
Thank you.
All right, moving on. Okay, so the roadmap for Unit 7. So remember talking about like, what's our sequence of events? Where are we starting? Where are we ending? Here it is. Here's the roadmap. So we're going to start with a unit opener, which really, and we'll talk more about it in a second, but really the unit opener introduces us to kind of two different ways to think about heat energy: the physical transfer of heat energy and the chemical production of heat energy. And so they're kind of two different parallel paths. And so the different task sets focus on different things. So we jump right into fuel analysis, which does have us talking mostly about chemical production. And then we get into urban heat islands, which has us doing mostly physical. So we have both happening in the same unit. Then we have our assessment, and then we have our engineering project. Task set 4 and task set 5, I feel like are, if you really want to do the engineering project first and the assessment later, you could swap those. Often we like to do the assessment first, and then we can really kind of focus on the iterative nature of the engineering project, and we're still applying what we've learned, but we don't have that assessment hanging over us like, oh, that's coming. I gotta think about that. We can really just give our attention to the engineering project. All right, so the opener, that's where the phenomenon is introduced. So we often have slides that we start with on the unit opener, so you can see that we start off right away thinking about how does heat move. So we have these different images. What makes heat increase or decrease? What do we notice about where these people are sitting? All of these different, what do you notice? What do you wonder, right? And then then we start going into some activities. I really love this one where we have two thermometers, and they've been sitting in the same room for a while. And then we place one of the thermometers into the glove, and the other one remains where it's been sitting this whole time. And so then we ask the students, well, what happens to the thermometer? Like, what happens to the reading after it's been sitting in the glove for 30 minutes? And so people talk about that and brainstorm ideas, and then they make a prediction. Okay. Then we go on and do some other things. So the next thing is we're drawing a model. We have a lot of emphasis on modeling in chemistry. So always trying to take our ideas and put them into a visual form. So what do we think the particles are doing in the thermometer? What do we think they're doing outside in the room or in the glove, the particles around the thermometer in the glove? What do we think that looks like? And we've drawn lots of models like this over the year, right? So kids are very well versed in how to draw a model. They're well versed in thinking about systems in terms of like what's happening inside, what's happening around. So they should be pretty proficient here in terms of being able to draw their thinking at this point, right? Because we've practiced it so many times. All right. Now, I love to do this one. So reach around. I tell my students, take your right hand and reach around behind you and grab the leg of your chair. Just feel what that feels like. And then take your other hand and put it on your desk and feel what that feels like. And so often kids will say, like, they're grabbing the metal leg of their chair, right? So they're like, oh, the leg is cold and the top of my desk is warm. So then we say like, well, that's weird. Why is that happening? Well, metal's just cold. Okay. Well, how aren't they sitting in the same room? Yeah. Haven't they been sitting in the same room all day? Yeah. So wouldn't they be the same temperature? Well, no, because the leg feels cold, right? So that's when we get the temperature gun out and show them, well, the leg of the chair is actually the same temperature as the top of your desk, which is actually the same temperature as the floor, which is actually the same temperature as the lab bench, et cetera, et cetera. And so then we really start activating thinking like, why is that happening? Why does that one feel colder if they're actually the same temperature? So kind of getting that going. And then we show this video. And this is a Veritasium video where he's walking around this like street fair. Um, I don't know where he is, but he's walking around and he's asking people questions about, well, I'm going to put this ice cube on this metal block, and then I'm going to put another one on a plastic block. And which one do you think is going to melt faster? And just like it's fascinating looking at people's responses and why do they think that? And it's a great video. It's one of my favorites. And it's kind of getting at this, right? It's getting at the same idea. Why does that leg feel colder? So we watch the video and then we kind of discuss together as a class what's happening. And we thought about how an object feels. How is heat moving when an object feels cold? Why did the ice cube melt faster on the aluminum block than on the plastic block? So after all of that discussion and having the opportunity to check in with your elbow partner about it, then we populate this together. We come up with the answers together. And then here's the important part. At the very bottom, now take a minute to think of a question you have and write it on a sticky note and put that sticky note on your desk. What are you wondering about right now? And then we move on and we introduce the unit question. We start thinking about, okay, we looked at how heat moves. We looked at the rate of heat transfer. Awesome. How does that connect with fuels? Because then we start talking about how, what kind of fuel do we use? This one happens to be for the US. Like, what kind of fuel are we using in the US? And then, I believe this one, oh, this is world energy supply. I love this one. Like, what are people using around the world? This one is Europe here, but what kind of fuel are people using around the world? And then more about fuel consumption around the world. And then just like, where do fossil fuels come from at all? This is a short video talking about where it comes from. And then we kind of focus in on 3 different kinds of fossil fuels. And then again, we pause, take a minute, write down a question that you have, put it on a sticky note and put it on your desk. So now at this point, they should have 2 questions. Then we come back to the glove. We take the thermometer out of the glove and we check the reading and we see what happens. And then we go back and we make any adjustments to our model. So now that we have more information, now that we have more data, is there something that we would change about our model? Give them the opportunity to do that. And then come back to the 2 big ideas. How does heat move? What do we know about fuels? Kind of thinking about those side by side. They feel like different things, but are they connected? Right? That's what we kind of want them to think about. Introducing the project for the end of the unit, which is about designing a cooling space. So one potential cooling space could be a deck. I just grabbed this off the internet. There's lots of images on the internet about decks, but it doesn't have to be. We decided to make it a cooling space rather than talking about a deck because not everybody has a deck, right? So we just made it in general that if it's hot out and I want to have a space that's cool for me, how can I design that? How can I create that? Then we come back to the questions that we've written. So we have 2 questions that we've written. Can you think of a 3rd question that includes ideas from the first 2? and connects to our final project. So I'm going to think about my 2 stickies, and I'm going to think about the final project, and I'm going to see if I can write a question that encompasses all 3 of those. I'm going to share my questions out at my table, and the table's going to come up with, okay, which question do we feel like is the best question? And that's the one that we're going to use for our driving question board. If you haven't tried a driving question board, I highly recommend it because it is, it's an amazing opportunity to really get the kids to engage in their own wonderings, engage in their own ability to ask questions. And it shouldn't be questions that have a yes or no answer. It shouldn't be a question that we can just quickly Google a response. Like, we want them to be deep thinking about the questions. And that's why we kind of pace it out through the whole opener, right? We do some kind of activity, some kind of hands-on, then we pause and we write a question. And then we do some more stuff, and then we pause and we write a question. And then towards the end, we kind of take all of those pieces and can we write a better question that encompasses all of those pieces? So this is an example of, this is actually for Unit 4, but this is how I use driving question board in my classroom. So each on the left, those 3 different colors are for 3 different class periods. And so they have the same scene on each one. I had my middle school daughter help me draw the scene because I am not a drawer. But she drew it, and then I had students put the sticky note, their question, where they best thought that it fit. So sorry, the one on the right is for Unit 4, and the one on the left is for Unit 1. So whatever you make your background visual, and some people don't even draw a picture, they just use stickies and they put it up on paper. Awesome too. The whole point is for students to kind of engage in thinking around what questions do I have and what constitutes a good question. And by good, I mean not a yes or no and not a quick Google answer if I Googled it, right? It's a deeper question. And I usually early in the year, I give them some examples and non-examples just to try to focus in on that ability to ask good questions. But by the time we get to Unit 7, they've got it pretty well dialed in. How are we doing so far, Andrea? Any questions come up?
No, and everything's been, people are just following along. I want to just, nothing's coming up. I'll let you know if they do.
Okay, perfect. So I just wanted to show you quickly what a teacher notes looks like. So this is task set 1. Remember, these are all in the restricted files. So we always start with our essential question. What's our phenomenon? Here are our practices, our 3D practices that we're focusing on. And then we really go into a lot of detail in the lesson flow section. And the length of this varies depending on the complexity of the task set, but the point is really to provide a lot of teacher detail that's relevant to the teacher. Because sometimes when somebody else writes lesson plans, or at least this has been my experience, when somebody else writes lesson plans, it's like I kind of get the gist, but I don't have the full complete picture. And that's because it's in their head and not in my head, right? And so the teacher notes try to really address that by doing a lot of the explaining about what's going on. But I will tell you the hands down best way to really get the gist of it is to attend the in-person summer class, because we go through the activities together and you are often doing the role of the student where you're seeing it for the first time and doing it. And then we do a class discussion together. Like, we go through and model all of the different pieces so that you're kind of seeing it from both sides. You know, we pause and look at it from the teacher perspective, and then we're also looking at it from the student perspective. So you can see what students would be dealing with, what they're interacting with, and you can anticipate the kinds of questions they'll have, etc. So just a little plug for our summer course. It gives you an idea about how long it should take, any additional notes that we have. If students are absent, what can they do? What are our suggestions for what they can do? So this is the kind of information that's in our teacher notes. And remember, this is only available in the restricted folder. So Andrea had the link for that. I believe it's in the chat. And so if you do not have access, go ahead and fill that out and we will work on getting you some access.
And if you still need it, just drop a note in the chat and I'll put it again.
All right, we looked at that. Okay, so just to, again, when you are creating a driving question board, we're starting with something that students can experience, right? They're either looking at it or they're watching something. Like we had some images, we had our glove and our thermometer, we were drawing some models, we were grabbing our chair and putting our hand on our desk and noticing and doing some observing. They have to have some sort of a engagement at some level in order to be able to wonder and notice things, right? So if we're asking them to notice and wonder, and ultimately we're asking them to write some questions, they have to have something to engage with it, right? We just talked about that. So then students have post-it notes, they're writing down questions, and we've already spent time early on talking about what's a good question, what's not a good question, looking at some examples and non-examples. And then as students bring their question to the poster, they're reading it aloud. And then the next group can either build on what the previous group's question was, or they can go in a whole other direction. Either one is okay. And then you can group the questions by common themes if you like. You can also not do that. But what's particularly powerful about the driving question board, what I really love about it, besides the developing the skill of asking questions. I think that's a key piece. But also it's when you come back to it periodically. Like you can't just do it at the beginning and then that's good and we're never going to talk about it again, right? You have to keep coming back to the driving question board. Okay, what can we answer now? Now that we've done some learning, which of these questions can we answer? So you can kind of go through and as you answer them, you can, so people do this in different way. What I like to have is like a see-through bucket that has a label on the front, questions that we've answered or something like that. And then as you're finishing, you're putting it in this see-through bucket. So over time, you're seeing like all these post-it notes in a bucket and it's very motivating for students who are like, I was wondering this, I had these questions, oh my gosh, we can answer it. Now, just feeling so accomplished about it. And it's a celebration too, like it's a celebration of knowledge. As we continue on through our unit, we're learning so much and we're able to answer all these questions and we could go home and we could tell our families about it. So just trying to celebrate that aspect of it. And then sometimes there's some questions, they're beyond the scope of what we're learning about, or they're a sidetrack. That's okay. Students can ask those questions. They should. But sometimes our answer has to be, gosh, that is beyond the scope, but how could we investigate that? Or how could we go about, collecting some information to be able to answer it? And just letting them do a little bit of that brainstorming and thinking before we move on. So that always felt like an unsatisfactory answer to me when I first started doing driving question boards. Like I felt like I really had to answer all the questions. We have to answer it. And what if they ask me something I don't know the answer? And I hope they do, right? Because that's a great thing when students ask questions and you're also modeling like I don't always know all the answers. That's okay that I don't know the answers. But you know what? The way scientists go about finding information, it's pretty common. It's a pretty common way, common system of doing it. So even if we don't know the answer, and maybe it's even beyond the scope of our unit, a person could continue on and keep investigating. And that's a good thing. It's a good thing to do. And I love that you thought about that question. Remember, it's about the celebrating, right? Celebrating that not only are we finding answers, but we're also asking really good questions because that's part of being a scientist is asking really good questions. So, okay, I will get off my soapbox now about driving question boards. They're one of my favorite things ever, if you haven't noticed. All right. So takeaways from test set 1, which is all about the unit opener. We're just looking at how heat moves. We're looking at heat transference, and we're thinking about fuels. And then I know we're doing this project at the end about a heating and cooling space. So like potentially, how could those be related? Just getting my thinking going about that. All right, that's what test set 1 is always about, engaging in the phenomenon and getting our questions going. All right, test set 2, fuels analysis. This is a big lab. We've done some updates on it, but it's still a big lab. There's a lot to it. There's a lot in it. And always we have some slides, and then we have our student template, and then we have something new this year, which is the shared data table. And I do see that Mr. Matt Randall is here, who did quite a bit of reworking of these activities. And so, hi, Matt. So if you want to jump in and do some talking, I'm happy to do that, or I can start and you can hop in whenever you want, whatever you want to do.
I think, can you start and I'll just hop in
Yes, I will
at some
do
point.
that.
Awesome.
Okay. So starting with the fuels lab, we are getting them going on thinking about some different fuels that we'll be testing. So we have paraffin wax, soy wax, isopropanol, and ethanol. And we're trying to think about, so the two questions at the bottom, which of these fuels do you think produces the most energy per gram? So kilojoules per gram, the most energy per gram of fuel combusted. And then which fuel is the greatest contributor to climate change? So which one's like the most efficient for getting the most bang for our buck, if you will, like the most energy per gram? And then also, which one's contributing the most to climate change? So those are kind of like, I imagine they could feel conflicting potentially. Like I want a really efficient fuel, but I also don't want to make a lot of CO2. So how do we sort of balance those things? And then we start thinking here about calorimetry. So this is about our physical transfer of heat energy, right? So negative Q equals Q. And then there's a couple of ways you could go from here. So you could do metals or other objects, which is kind of the classic calorimetry experiment, solving for the heat capacity of the metal or really any variable in there. But there's also another way that many teachers have gone where they're burning some kind of an oily, fatty food, like a Cheeto or some kind of a chip, right? So it's that oil that's combusting in there, and then you're heating up water, and you are trying to figure out how much the water heated up for how many. Matt, you weigh the Cheeto before and after, right? So how much of it burned, and then
Yep.
how much energy was produced.
Yep.
So a couple different ways that you could go from there, but just thinking about if you do the metal or the other types of materials, the calorimetry, that's more about the physical transfer of heat energy versus the Cheeto, which is combusting the oil in there, which is the chemical. So it's something to think about. And then we work through some calculations, and then we start talking about, okay, well, what's the setup going to look like when we are combusting the 4 different fuels? And remember, we're trying to answer those 2 questions. Which one gives us the most kilojoules per gram, and which one contributes to climate change the most? So this is going to be our setup. Thinking about lab safety, I love this slide. And then kind of going through the process of what are the pieces involved. And that is kind of day 1. It takes us all the way through day 1. And then as we go into day 2, this is where we start to do some new information that we haven't done yet in the unit. And that is, excuse me, to do the bond analysis here and calculate how much energy should be produced. So reminder about balancing, and then thinking about, well, this is still just about balancing, but eventually we're going to get down to this where we're thinking about what kinds of bonds are present and then how much energy is associated with each bond. And then coming up with a sum at the end. So the total amount of energy for bonds broken and the total amount of energy for bonds formed. And the more visuals you can provide about that, you know, what does that mean? CC bonds. Oh, well, it's here to here. There's 1, 2, 3, etc. Like working through a full example with students so that they can visualize what we're talking about. Because we haven't done this yet so far this year. We haven't really thought about the amount of energy at just the bond level, right? Still walking through our calculation for Q reaction, and then calculating the theoretical efficiency of your fuel. So we have our kilojoules per mole here, and ultimately, again, think of one of the original questions, how much energy per gram of fuel? So this is where we're calculating that. We're going from our kilojoules per mole and converting that into kilojoules per gram. It's always, I also find this conversation fascinating with students. Like I like to ask them, like, why do we have to go to kilojoules per gram? Like, what is the purpose of that? Why do we even bother? Can't we just have this and call it good, right? And so it's a great way to kind of get to a common point of, in order to compare them, we have to be talking about all of the same unit. Like we have to be able to compare the same thing. And so we have to put them all per gram so that we can compare all of them. Otherwise, we would be trying to compare things that are not the same, not similar. Looking at percent error, and then calculating the CO2 production. So getting back to the climate change part, how are we figuring out how much CO2 is involved? If I know how much energy per mole, how do I get to CO2? So we have to look at a mole ratio in there. And then revisiting fossil fuels, having our data discussion. And then I believe these are some more examples. Matt, what would you add to that?
Yeah, thanks. Maybe I'll just talk right now about the data discussion, and then I have a few things to add about just kind of the procedure. So we had students we have them do 4 different fuels, and then in their lab document at the end, well, I guess here, the data discussion conclusion, and then the next slide, if you want to go there, students are doing a gallery walk where each team makes a pretty quick whiteboard summarizing this. Shows the chemical reaction, the balanced chemical equation, their theoretical kilojoules per gram, so the efficiency, what we're calling the efficiency, the climate impact, which is how many milliliters of CO2 are produced per kilojoule. And we had a little discussion, like Joe Maynard talked about, like, why doing that? And like for our team, we just chose volume of gas. Usually it's measured in like this climate impact, we think of it in tons of CO2, or anyway, in like grams, basically. And this was just, we just wanted them to use molar gas volume so that they're doing different types of calculations. So, but anyway, milliliters of CO2 per kilojoule, and then sort like where does it come from? And then specifically if it's renewable or non-renewable. Yeah, and then the idea is that students are walking around and gathering the main information from the whiteboard, and then that's what goes on the table below. So the very next slide. And then we already have a few, like kind of calling back to your unit opener, like the main fuels that we burn for transportation or for heating or for electricity are gasoline, methane, and coal. Methane is the main thing in natural gas. And so this includes information about that. And then the other fuels that students studied are there. So we're kind of filling out this, we're using the gallery walk to fill out a large table. And then I'm not sure, does the next slide kind of have the CER? Yeah. And then for the CER, they're kind of, the idea is for them to look at all of that data and then to decide like which fuel, and I'm going to back up a little bit. We in like ninth grade science, when I love one of the things that like I'm here just is I love the connection to what we learned in ninth grade physics about, especially our unit 6, our energy unit, and thinking about like how do we transition away from burning fossil fuels to produce electricity. But then part of the thinking here is that it will likely still be necessary in a society to keep burning fuels for some things. And so which fuels should we are the best? Like if when we need to burn fuels, which ones are the best to use? Or even this connects to in ninth grade, they in patterns physics, they learn that many states are transitioning away from burning coal and burning more natural gas. So just like a trade-off. And this is why, like it's a nice, it's a transition where you can produce less CO2. It's about half as much CO2 per kilojoule that you produce. So it's not maybe not a great long-term solution, but it's a good like short-term solution. So anyway, that like going back to that table, then students are making a choice about which fuel do they think is the best fuel for our society to burn for those reasons, and considering whether it's renewable or non-renewable, and then the efficiency and the climate impact. And we're not really intending for one specific answer necessarily, but just that students are thinking about what those things mean. And so we, in my class, we like, as Chrissy mentioned, the efficiency is connected. We connect that to the cost, right? And this is, you might think about like, there's the like weight of the fuel that you're transporting around. You're paying for the, you're paying in energy for the transportation. You're paying in energy for the production of that, however you're doing it, from crops or from mining it. So like that number is related to the cost, and that matters for us as a society. And then the climate impact, the amount of CO2 that it produces, that also matters towards climate change. And so students might choose, like, I think I should choose this one because we have a discussion in class and we narrow it down to it should be a renewable fuel, because that way we're not adding new CO2 to the atmosphere. So like of the renewable ones, either which one is the cheapest or which one has, puts the least amount of CO2 back into our atmosphere for kind of bang for your buck one way or the other.
And I like how students they're not necessarily all arriving at the same answer,
Yeah.
right? They have to make a decision and then back it up with the evidence from this table. And it's just interesting to read through the CERs and see their thinking, their thought processes for what is better, what's a better
Yeah.
fuel. Well, what do we mean by that, and why do I feel like this aspect is more impactful than this aspect? So I like it when we don't all end up in the same place, because I think it's a rich conversation when we don't.
Yeah. And then it really calls back through so many trade-offs. I could talk about how it connects back to Unit 6 in patterns physics, but thinking about the trade-offs of different fuels is a
Yeah.
big too. So
Yeah.
And then I was gonna, if you're able
Yeah.
to click through the student lab template or open that
Yeah.
up, I'm gonna share a couple things about that. And
Absolutely.
then it's related, there's some related information in the teacher notes. But one thing I wanted to mention just in general, if you scroll down to the like setup is probably a lot of you or a lot of us have done different versions of calorimetry labs. And so I think, in my opinion, the exact like materials you use don't matter so much. You can, like I've seen very basic setups where you're just burning something underneath the soda can that's being held by a ring stand, or just underneath a beaker or an Erlenmeyer flask. And I think that can work fine. And then also the setup here includes like a metal can that's surrounding it. And so if you do look through the teacher notes, I have like instructions for how you could build them just using large metal cans, if that makes sense. And then another quick thing that I really like is if the container that we use for burning fuels is from tea candles. So if you just buy a set of like 8 to 10 tea candles, some of them you'll use for paraffin, and the others just pop out the tea candles, and then that can be your container for the liquid fuels that students are measuring by drop into their different containers. And then the improvements to the procedure, that part that we're kind of looking at right now, Also, I wrote in the teacher notes that this is something, there's a lot going on in this lab. And so this could definitely be something that you don't do. But this is a great opportunity for students to make small iterations to their experiment. So there's some labs that just lend themselves to making labs or projects like making small changes and then seeing how it affects. And so in the teacher notes, we describe some different materials that you could provide for your students. And then what we have them do is in between each of their trials, they use materials to try to capture more of the heat that was produced in combustion. And they're using the same, the same amount of fuel each time, and really like water, the same starting temperature. So they're pretty easily able to tell just from the change in temperature if they were able to capture more of the heat, if that makes sense. So it makes for a nice lab for them to be able to iterate in the middle. It's not super, it'd be better if we were doing like multiple trials, make a change, multiple trials, make a change. And we found that we just don't have time for that. So yeah, but it's the iteration part's really cool. And we gave students just a small set of different materials and they came up with lots of different things. And they end up connecting a whole bunch of different, they'd see other people do things, and then by the third trial, we had like a lot going on, and their percent errors were getting, I think we're still losing half of the heat. But they were going, percent error of like 60% was going down to 40%,
Nice.
so they were
Nice.
very noticeable changes in that.
I know that
The other-
when we ran this lab
Mhm.
in my classroom a while back, the part that had the most engagement from students was the part about reiterating it to make it be better, because it's something that they can feel and see a difference, because they can feel the heat coming off when it's not supposed to. And so they can like, but what if I put aluminum foil here? Or what if I
Yeah.
so it's definitely the most engaging part of the lab, except for maybe burning food.
Yeah.
Mhm.
If you do the burning food at the beginning, kind of stay away. Be careful with some of the puffed Cheetos. They make a lot of smoke. But yeah, no, this was the most
Yeah.
engaging part.
And I
Yeah.
would say just building on that, if you wanted to differentiate this activity a little bit, a great way would be to quantify, if you can quantify the loss of heat, because in most cases we're losing heat, not gaining. And so not to a specific amount, but just making the connection between what is the source of error, how did that affect my measurements, and then how did that affect my calculated value, my result, and just kind of quantifying it there, like it made it larger or it made it smaller, is a great way. Often that can be kind of mathematical, which makes it, I think, a great way to differentiate the thinking behind the error analysis, the iteration, and the kind of open-ended inquiry about that. Like, what if I tried foil versus what if I tried wax paper? Whatever. That's another way to do it. But if you were looking for a way to differentiate it, one could do it that way. Matt, do you want to talk about the sheet?
Yeah, and so the next thing I wanted to talk about just briefly is we tried to build in a lot of different scaffolds for this. So another reason that I really like this as a lab is that it's putting together a whole lot of skills from this, especially the whole like all of our second semester topics. And so, but one thing for you to think about as a teacher is some of these scaffolds you might decide that you don't want to use. Like you feel it would be better for students to do more of it on their own. And so this is an example where this is a data table where students can use to enter their data as a team. And then at least this one is coded already so that the calculations are being, like, as they're making the measurements, the final calculations of how much like the thermal energy of the water increased and so much heat, roughly how much heat was produced by the combustion reaction, and then dividing that heat per gram of fuel used. Those calculations are coded in here. And so in my case, for example, I teach our inclusion classes at school. I have about like more than half the semester of my students are students with special needs. And so this is the version that I plan to use. And the main goal is that we can get to the stoichiometry and then the claim evidence reasoning, that we can make that the main thing. and not so much the calculations. And there's
The
a number
math,
of little
yeah.
places where they can get stuck and get, you know,
Mhm.
like their whole thing can get thrown off. And that's what, you know, where as teachers are walking around, we're helping them and trying to help them understand. But the goal of this is to help get to the main point. But you might also decide not to use this and just have students type in there, like to not have the coded parts, if that makes sense,
Mhm.
and just have students calculate it. And I have a colleague that doesn't teach our inclusion classes, and that's what they do, if that makes sense. So it's we choose to do this differently, but we're still using the same. Our students are still doing the same overall thing.
Right. It's just what do you want to give time and emphasis to?
Yeah.
I remember when I was teaching it, I really didn't want students to think that, you know, there's a black box and this like math is happening behind this black box, and then I come out with this answer. Like, I wanted them to know, how are we arriving at that? But if you want to stick to kind of the bigger picture of fuel efficiency and climate change, you know, having a coded sheet is ideal, right? So it just kind of depends on what do you want your focus and emphasis to be. Um, and I love that we try to offer options in our task sets. Like, if you have more time or you want to focus on this, you could go this way. And if you have,
Yep.
you know, whatever. Ultimately, it's teacher's choice, and you know your audience best. So whatever makes the most sense.
Cool. And if you go back to the lab doc, I just want to talk a little bit about the analysis questions. So if we scroll down in the calculations, and again, this has a number of scaffolds that are built in. So actually going back up, one of the scaffolds is just that box to help students count atoms. So one more, just question one.
Oh, one more. Gotcha.
Yeah,
Thank you.
sorry. Box is not very descriptive, but
Here.
the balance equation. Thank you. But just having like the not having to balance in your head or like kind of write on scratch paper, but having a place for students to physically like count the number of atoms. That's what the C, H, and O boxes are, left and right, and then using that for balancing the equation. And then next, the Google Drawings part, and we'll just kind of see an example. Each of these, this one is like finished. I plan to change this to gasoline. Last year, we tried lamp oil and then decided it was not a good thing to burn indoors. So I just did it for one class period and then not after that. But anyway, the way that these are set up, and you can scroll down to one of the next examples, is just that the basic reactants and products are in there, and then students can use the coefficients of their balance equation to make a visual representation of this, of what's happening in the reaction, and then use this to help count the number of bonds. And then for the large molecules, the number of CC and CH bonds, for example, are already listed on so paraffin wax, just so that we're not spending, it's another kind of just, you know, they can count those, but it's also just really common for kids to be off by a little bit and then the results aren't quite right. And that's not like spending the time counting all of those is not the goal.
Well, and if you think about back to the slides, like, we want to populate that slide at the end where we have our 4 fuels, and we want to look at renewable or not and how efficient, because they're going to use that slide to ultimately make a claim for their CER and back it up. And you could imagine, if you make a mistake in this box counting how many bonds there are, then all of your results after that are going to be off. And then potentially we're not going to have accurate results to look at. So then we may be drawing conclusions that are not you know what I mean? Like,
100%. I totally agree.
we don't, just like Matt said, I don't think we want to spend all this time like counting tiny individual bonds, especially when you have large coefficients. It's just maybe one together.
Yeah.
Right? Modeling one together. And then, like Matt was saying, and then just give it to them after that, you know, at least for the very large molecules.
Yeah.
Well, for an earlier version of this, we did have students count them, at least in my classroom, and some of them got it, and some of them got so frustrated that they were like, I give up, the science doesn't work anymore. I give up on science, right? So we don't want them to give up on science. We want them to get the point that, hey, all these bonds breaking and forming is what's making all this energy.
Mm-hmm. Yeah, and then just kind of briefly, same thing with these like 3 and 4, and then 5 and 7, if we can look at just the stoichiometry calculations, providing a table and some instructions for students. I think you could definitely like get rid of some of the right. I think like a higher level task would be to give students the starting units and then the ending units, and then they figure out right all the units in between. And that's like for, I would say that's like proficient in my classes. But again, here the goal is not to demonstrate, I would say, like advanced understanding of stoichiometry. It's one of the skills that we're using. We're trying to really help them give enough supports that they're going to get to an accurate conclusion or an accurate like calculation successfully, and then we can like have those discussions through the data discussion. So.
And remember, we've just come from stoichiometry, right? So this, hopefully, they are well versed in this, like they're comfortable, they've seen this before. So just like Matt was saying, a way to differentiate this is I just give them this and I say, and now we want this.
Yeah.
Go find that, go. Yeah. And then if I need to differentiate in a more structured way for some of my students, and maybe I give them this, right? So just depending on what you need to support your students.
Yeah. And I like in the Google Classroom, it takes time and thought and anyway, it takes time, but like we often do have different versions for our students with special needs that have more of the supports embedded in their actual document. But then everyone is working on everyone is working on it. They don't notice, right? It's kind of the same they're just looking at their screen and then doing a stoichiometry calculation. And so just something to consider. We try to have a lot of supports here, and then you can decide how much you want to use.
Great. Thanks. Let's do a check-in. Any questions about the fuels lab that we can answer? Keeping an eye on the chat. Okay, well, if you think of one, go ahead and throw it in the chat. Thanks for the scaffolds, Pam says. Thank you, Matt. Yeah. All right, moving forward.
I'm going to head out, everybody, but thanks for having me.
Thanks for coming.
The rest of the webinar.
See you later.
Thanks for dropping by.
Yep.
Task set 2 takeaways. So again, there's a lot going on in there. So we're looking at folding in our what we know about mole conversions, what we learned in Unit 6 about mole conversions, but now we're doing a new conversion. So we're doing energy per mole or using mole ratio to get from the fuel to the carbon dioxide when we talk about climate change, a polluter for climate change. We're looking at reaction types and balancing. We're thinking about energy in versus energy out. And we're looking at the net energy in a reaction. And then we have to put things in like terms. So if we want to compare them, they have to be in like terms. So kilojoules per gram is the way that we put them in like terms. So there's a lot going on there. All right, task set 3. This is a high interest topic, at least it has been in the past for my students, because everyone can identify with this, right? Everyone has an understanding of when it's hot outside, what you try to do to cool yourself down, right? They may not have seen it in maps like this before, but they all have something to say about this phenomenon. They all get it at some level. So we look at what are urban heat islands, what are some efforts to mitigate the problem, and what kind of impact does it have on communities? All right, linked in the teacher notes is this NASA interactive, which is great. So first thing I noticed when I came here was notice the 5E up here, which is the same way that our unit plans are organized: engage, explore, explain, elaborate, etc. And when you go in here, and anyone can go into this site and click around and see, you don't have to be a member of anything or whatever, it's for public use. And what I like about it is there's this part. Where have we seen this before? Anybody know off the top of your head what unit do we explore this in? Anyone know? Geosphere, biosphere, atmosphere. Just keeping my eye on the chat.
Hey, somebody's got it. Amy Elmert wins the prize and Pam Chambers is
Good
second.
job. Good job. Yes. With the climate change project, we look at spheres. So once again, it's like coming back full circle. We started the year with this. Now we're kind of wrapping up the year with this. So that's one thing I love about it. And then this, what it goes through and talks about kind of what it is, but then it also, at the end here, there is designing a cooling space, which is similar to what we're doing in the unit plan, but it talks about the cooling space as there's a marathon race that's happening and you want to sit and watch the marathon race, but it's too hot to just sit out in the exposed sun. So like, what can you do to help yourself be comfortable the whole time you're sitting there watching the marathon race? So same kind of thing, same kind of thinking, but just slightly different context. But anyway, this has, I can't click on it because this is just a screenshot, but there's a couple of tabs in here where there's a map like this one, and then there's a magnifying glass, and you can move the magnifying glass around, and then you can like, why is this really red right here? And I can use the magnifying glass to look really closely at this, and then I can figure out what's going on exactly in these spots that make it fully red. So sometimes it'll be like there's a parking lot there, or there's some big concrete something building, whatever. And then kids can start to make the connection like, oh, I see. So it kind of depends on what the material is, and like, why is this one super green right here? And you use the magnifying glass and it's like, oh, well, there's a lot of trees and stuff right there, right? So they start to make those connections. So this is a great one to just get in and click around and explore. So here we're just kind of learning generally about what are urban heat islands. There's lots of images in the slides for people to think about. There's several Portland maps in there. So if you are not from Portland, you might consider doing a little hunting around, like, is there a heat map for the area that you live? And then swap out the Portland one for the one where you live. And just to make it contextual for like, this is where we are and this is what our heat maps look like. We found all of those on the internet. They are widely available. So just you could do a little digging around. And then what are cities doing? This one's super interesting. What are cities doing to try to reduce that effect, that urban heat island effect? What are some things? And as I drive around Portland, I can see lots of instances where the city is trying to address urban heat island effect. But it's just, again, if you can find instances in the area that you live, it'd be interesting to point those out, because sometimes students haven't ever considered that or haven't looked at it before.
That just in support of your idea of trying to swap out the maps for the ones for your local area, students get really jazzed when they start thinking like, wait, I was there the other day and it was a lot hotter. Like, it really relates to their own experience and makes them more engaged.
Agree. And then I'm thinking back to the original unit opener slides, like the very first slide, second slide, where there was the picture of the people at the concert, and like, where were they sitting? In the shade provided by the pole, or the people who are waiting in line on the sidewalk, and then they have that cover over the top of them, and it was shaded underneath, and like, just how much relief a small thing like that can make is significant. And having kids like share stories about what's something that they've done in the past or something they've seen, or because again, everyone can identify with this issue, right? Every single kid has some experience with trying to do something to cool themselves down, right? Whatever that is. All right, so the unit for assessment, we are still in process. of doing some work on our assessment, and this is true across all of our units. This is another summer project, is to really dig in and do some kind of deep analysis and deep thought on our assessments being three-dimensional. So how can we get not only DCIs, but how can we get our science and engineering practices and our cross-cutting concepts folded in to a question? How can a question kind of envelop all three of those? They're hard to write sometimes. And so we're going to give some good time in the summer to either retooling some of the assessments that we already have for previous units, or in the case of Unit 7, putting together an example assessment that really has some good 3D questions in it. So still to come. We're working on a test bank also, where there's multiple 3D question options depending on, and they're scaffolded in different ways. So depending on the audience that you have, you may choose different question types. And then also an alternative assessment. So one option is you could use the engineering project as the unit assessment. So instead of doing a paper and pencil test, maybe the engineering project or one of the shorter projects, that is your unit assessment. So just an idea there. Okay, so now we're getting to task set 5, which is the engineering projects. So how we're looking carefully here at how well different materials transfer energy to the air, which is all about developing a good cooling space. So the things that we put into the cooling space have a direct impact on how comfortable that cooling space is, or like how much it raises or lowers the temperature. So what students are going to do is an investigation into different kinds of materials, not unlike our, if you did the calorimetry experiment early on with different metals, and maybe even tried different materials instead of just metals, but not unlike that, right? So similar. Okay, so the longer engineering project has 4 main parts. So we're starting with a CER at the beginning, which is identifying what is the problem and what are we constrained by. What do we need our solution to do, and how are we limited by it? And from there, then we go into investigating the parameters affecting energy transference. So if you can't tell, this is a styrofoam box. And then in the box, we have a thermometer. And then the idea is we put different materials in this and cover it up, and we see how does the temperature change over time. And so if I fill it with like, and we're also heating it up. So we're heating up the box, we're heating up the material. So we have a little heat lamp on it, and we shine it on there for a particular amount of time. Then we take the heat lamp out, close it up, and then we look at how the temperature changes over time. And so like if I put a bunch of rocks in here versus a bunch of palm leaves or something, I'm going to notice a difference in my temperature change. Right. And so that's the idea here is we're just trying different materials, and then we're looking at how does the temperature change over time. And with that information, then we are designing a solution. So we're trying to get at our cooling space or our park or whatever it is. So here's an example. And how are we creating kind of that cooling space? What kinds of materials do we want around us? And we're going to draw directly from our experimentation. And again, part 1 is identifying the problem and the criterion constraints, but there's also, we're looking at, well, how does heat from the sun, how does that warm the planet? So again, this is a little bit of revisiting Unit 1 when we did a greenhouse effect, right? Because we studied this in Unit 1. So the energy comes in and some of it bounces off, some of it goes right through, and some of it bounces back down and warms the earth, right? And we rely on this so that we can exist on this planet. But if we change the environment, if we change the materials, does that impact how much or how little the surrounding air heats up? And it turns out, yes, it does. And then the evidence for that is right here. There are a few shorter projects too. So if you're kind of pushing up against the end of the year and you don't have enough time to do a 3 to 4 day project, you can consider one of these 4 shorter projects. And we are, so one of the projects is just investigating biofuels a little bit more. This is a little bit more like a research project. This one is more of an experimental project. So there is a defrosting tray here. And let's say you have some meat that you need to defrost. What material is best for the defrosting tray? So students have to design an experiment where they try different materials and they come up with which material is best. There is designing an urban heat island. And again, thinking about sorry, not designing an urban heat island, but mitigating the effects of an urban heat island. So if I were creating like a patio space, what materials would I use? And then thinking about an insulated water bottle. How is that made? Like, how does it keep cold things cold and hot things hot? And designing an experiment to test those things. And not only to test them, but you're designing really your own insulated cup is what it's called. You're designing your own insulated cup and then testing it, testing the materials that you've used in the design to see how well it keeps cold things cold and hot things hot. Not unlike an insulated water bottle, right? But you're designing your own cup here. I've done all 4 of these with my students and had such great success. Unit 7 is super engaging for kids because it's all about heat energy, and that's something that everybody has experience with. It's not a crazy far out reach for students. Like they have experience, they have something to contribute, they have something to say, right? Because they've all, engaged with it in some way or another. So that is an option as well. Here's a couple of examples of student work that I wanted to include. So these 2 are this one right here. So how to create a like a cooling space, a patio or just a cooling space. So they've gone through and they've talked about the different materials that they would use. I usually have them write something. So they've drawn the image, but then also, why did you choose wood here? Like, what is your evidence to support that wood is a good choice? Why is this made of polycarbonate, for example? So they have to do a little bit of writing about it. Let's look at some of these down here. So here's someone's made a slideshow and they go through, remember I was talking about the marathon and you're designing a cooling space for yourself. So this student used, look, they made a cool grass hut to sit under while they are observing the runners as they go by, right? And so they go through and they talk about, well, why those materials? Well, first of all, what are urban heat islands? How is energy transferred, et cetera, et cetera. There's that magnifying glass I was talking about, right? So you could move that around and you could see what's underneath. This is this, right? So a lot of congestion there. And then right next to it is all this blue because that's all this green space. What are the problems caused by that? Ways to mitigate it. Included a couple videos. And then there's some resources here on albedo, specific heat capacity. There's a rubric, and then they do a works cited page. So this is an option. This is one of those 4 projects. Let's try this one. Yep, here's another one. So again, what are they? What's the problem with them? Ways to mitigate them. This person went in and talked more about the materials. So dark roof, a grass roof, a light roof, kind of what that means, what albedo means. Here's the race again. Works cited, reference information. So whatever material you choose, great, but you have to be able to back it up, right? Why did you choose what you chose? Last one. This one, I love this. They did a small particle model where they're looking at the air outside versus the air inside, right? And there's a concrete wall versus an eco shack wall. So they really come up with a lot of very clever things. And then that they went in and drew a small particle model or found something to simulate a small particle model. Fantastic. Love that. Looking at some real world examples, there's our Portland map. Just the impact in general of urban heat islands, workarounds and mitigation. So what different communities are doing, etc. So lots of great exploration that students do in these examples. And they're very self-directed. Like I gave them a structure and a framework for things that I want them to include, but where they went with that was kind of up to them. So I got a lot of great results from that. Here's another example of something that a student has designed. So again, what kind of material will it be made of? And then I have them write something in addition. Well, why is it wood? Why is there grass here? Why did you choose this shade sail, etc.? And I think this is the last one. Here's another example. Again, why did you choose these? And then the takeaways here, just really trying to, everybody again has an idea of why someone would need a cooling space, but the materials that we use to construct that cooling space have a big impact on whether the space is actually cooler or not. So what are the materials? Why did we choose them? What's our evidence to support that? And how do they go together? Right, is really kind of the takeaways from task set 5. All right, so let me pause there and see if we have any questions so far.
There's nothing in the chat, but if you guys have a question, feel free to unmute and ask or put it in the chat at this time.
Excellent. Thanks, Steve. So there's not a lot of task sets in this unit. Other units have more task sets, but each of these task sets is rich in that there's a lot in there. We've talked about the option of trying to break up task set 2 because there's a lot in there, like I was just saying, like maybe do a pull out calorimetry and do that as a separate task set, and then that builds into fuels. That's one of the things we're considering and kind of playing with that idea. But even though there's only 4 task sets, that still takes 3+ weeks to do this unit. I'm thinking 3+ weeks if meeting every other day in a block schedule. I think we said at the top, around 8 class periods. So there's a lot to do here. I mean, each one has a lot of days. Great. Okay. Well, let me show you what's coming up. I'm very excited to say that this summer we will be having our in-person courses. And not only that, but each section, chemistry, bio, and physics, are all offering 2 different in-person courses. So usually, for example, in chemistry in the summer, our course is units 1 and 2, right? We haven't done 3 for a long time, and then we never get to second semester units. And so the fact that we're able to offer 2 different courses and focus on different semesters is very exciting. I've been wanting to do this for a while now. And I will just say again, I think I've said this already, but the best way that I got on board with patterns and understanding the curriculum is by going to the summer class. Because again, the hands-on nature of it, seeing it from the student perspective, seeing it from the teacher perspective, and just like all the pieces fell into place, like, oh, I get it now. I get why we're doing it, and I get why we're doing it in this order, and I get the context, the bigger picture of the story that we're telling as we the phenomenon, how does it connect? So if you've not ever attended an in-person class, or if you've only done you know, the beginning units and you want to explore the later units, we're offering that for physics and chem and bio. So the dates are here. The biology one is in Hillsborough, and the chemistry and physics are both in Beaverton at the same location at Sunset High School. You'll notice that we're there at the same time, July 29th through August 2nd, and then chemistry's second course is the next week. And then physics is the week after that. So over kind of a 3-week period here, we're getting all 3 courses in. Sorry, I have a little tickle in my throat. All right, we do not have links for registration information yet. There's a few little things we're trying to work out. But keep an eye on your email. That's when the flyer will show up in your email, and it will have the registration links on it and more details. So all of that is coming up.
There was a question in the chat about the supply list, and we are working on updating the supply list, but I know that it's on our to-do list for the council, but I'm not sure that I have more of an update than that. I think we were planning on trying to get to that this summer.
Yes, we have a slightly updated one that we had to kind of put together in short order, but I think we want to go through it with a little bit more of a fine-tooth comb. So I think that's also a summer work, is to just perfect that a little bit better. Steve says that there's a pre-registration link. Oh, and he added it. Thank you so much, Steve. If you're interested and you just want to get your name down as a pre-register, you can click on that link in the chat and just let them know you're interested. Otherwise, I appreciate you being here today. I know we're ending a little bit early, but I'm sure no one's going to be upset about having some time back for their afternoon. And if you have questions, please stick around. Let's talk about them. If not, I appreciate you being here and taking some time out to talk about Unit 7. So it's a great unit. If you haven't done it, looking forward to hearing about your successes. Thanks, everyone. Great. Thank you. Excellent, Pam. I hope you do. It's a great unit. Thank you so much for coming. Appreciate you.
Thanks, Christy.
Yeah, thanks, Steve. Appreciate
That's
it.
good. And that that document is hot off the presses like 30 minutes ago.
Steve.
The pre-registration?
Yep. And
Excellent.
it's got the description for the workshops.
Oh, good. Okay.
So that is live.
Excellent. I have not seen that one yet. I'm going to click on it right now so we can take a look. Oh, okay. This is the flyer. Got it. Yep. So it does have, okay. When I looked today earlier, it was not updated. So this is the updated one. Excellent.
Yeah. So thank you so much.
Thank you. It's this pre-registration form. Okay. So we don't yet have the individual registration links. We still just have the pre. Okay. Got it.
Right.
Got it. Thanks, Steve. Appreciate it.
Have a great afternoon.
You too.
Thanks.
One new message. Let me scroll down there. Oh,
well, it's just about where people saying thank you, who are super nice. Yeah.
Thanks for coming. I see we have some people left though. Hello, Arg. Hello, Kathleen. Any questions that we can answer?